Section 10.1 is entitled Sequences as Functions. Let's define a few of our vocabulary terms here. A sequence is a set of numbers in a particular order. A term is any of those numbers in the sequence. A finite sequence contains a limited number of terms, hence the term finite, and an infinite sequence continues on without end. A sequence can be considered a function in which the domain is the position of each term and the range is the term itself. So for example, if we have the finite sequence 4, 8, 12, 16, the domain, remember, is the number of each term. So since 4 is in the first position, 8 is in the second position, 12 is in the third, and 16 is in the fourth position, the domain would be 1, 2, 3, and 4. Those refer to the positions of the numbers, and then the range is are the terms itself. An infinite sequence that would continue on, 4, 8, 12, 16, and so on, the domain would be all natural numbers, and the range would be the set of all y, such that y is a multiple of 4, y being greater than or equal to 4. Notice our first term is 4, and then each one goes up, 4 is multiplied by 4 to get the next term in the sequence. An arithmetic sequence has each term determined by adding a constant to the previous term. And the common difference is what we call that constant value that's added to each term. So the sequence is arithmetic if you're adding a number each time. Let's take a look at a couple examples here. Determine whether each sequence is arithmetic. So I have -3, -8, -13, -23. So is there a common difference? Is there a same number being added each time? Well, as I go from -3 to -8, I'm subtracting 5. And yes, I know I said adding, but you could think of that as adding a -5. As I go from 8 to -13, I'm subtracting 5. But as I go from -13 to -23, I'm subtracting 10. So no, this is not an arithmetic sequence. Because there is no common difference. If we had just continued subtracting 5 each time, it would be considered arithmetic, but it's not common. When we went from the third term to the fourth term, we actually subtracted 10. Let's take a look at our second example here. -8, -2, 4, and 10. So when I go from -8 to -2, I'm adding 6. From -2 to 4, I'm adding 6. And from 4 to 10, I'm adding 6. So yes, this is an arithmetic sequence. Because the common difference is 6. Actually, I think I'd like to say the common difference is a positive 6, adding 6 each time. Okay, here's another example. Find the next 4 terms of the arithmetic sequence and then graph it. So the first term is 10, and then 2, -6, and -14. First thing we want to do is find the common difference. So when I go from 10 to 2, I'm subtracting 8. From 2 to -6, I'm subtracting 8. -6 to -14, I'm subtracting 8. So my common difference is going to be a -8. So now I need to make a table of values. So I'm going to think of this as kind of like, what should be the best way? I think I'll do it this way. I have x and y. And remember, my x's are the positions, okay? So the first term is 10. My second term is 2. My third term is -6. My fourth term is -14. And then it said find the next 4 terms. So I need my 5th, 6th, 7th, and 8th terms. Okay? So I just have to keep subtracting 8 each time. So -14 minus 8 is a -22. It's going to give me a negative 30, a negative 38, and a negative 46. And now I need to graph this. And when I graph this, it's actually going to be a discrete function. It's going to be just a series of dots. I do not connect the lines, connect the dots to make a line. I just do the dots. So I think what I'm going to have to do is, on my x-axis, I'm going to have to go by 1s, and I think on my y-axis, I'm going to go by 5s. Let's see, so this is by 1s. Oops. And this will be by 5s. So the point 1, 10 is going to be 1, and then remember I'm counting 5, 10. 2 is going to be something right around there. It doesn't have to be super precise. 3, negative 6, so I'll go down 5 plus a little bit more. 4, negative 14. 6, oops, I forgot 5, negative 22, so there's 5, 10, 15, 20, and a little bit there. Whoops. And negative, let's see, what was I up to? 6. Sorry, but hold on a second. There we go. 1, 2, 3, 4, 5. Oh, I didn't get that one. 5, 22 is going to be about there. 6, 30. 5, 10, 15, 20, 25, 30. 7, 38. And 8 is going to be 46. Is that right? A little bit more than 9, something like that. Okay? So do not connect those. This is what the graph would look like, just a series of dots. And you'll notice that it kind of makes a line, which makes sense, because as x goes up by 1 each time, y goes down by 8. In addition to arithmetic sequences, we can also have a geometric sequence. And this is a sequence in which each term is determined by multiplying a non-zero constant by the previous term. So this time, instead of adding something each time, we're going to be multiplying something each time. And that constant value that's being multiplied is called the common ratio. So let's take a look at a couple examples here. Determine whether each sequence is geometric. Okay, so in other words, when I go from 8 to 20, am I multiplying by the same number as when I go from 20 to 25? The easiest way to do this is basically just divide. So 20 over 8, so 20 divided by 8 gives me 2.5. So that would be my common difference here. So when I go from 8 to 20, I'm multiplying by a 2.5. Okay, is that the same thing when I go from 20 to 50? 50 divided by 20 is also 2.5. So that common ratio exists here as well. I'm multiplying by 2.5. And let's check our last pair. 125 divided by 50 is also equal to 2.5. So it appears that yes, this is geometric. My common ratio is 2.5. Because that's what you multiply each number by to get the next. Okay, let's take a look at our second example here. So 1, 3, 7, and 15. So let's do that division. So 3 over 1, okay, is obviously equal to 3. Okay, so the common, or the ratio there would be times 3. Let's check the next one. 7 divided by 3. 7 divided by 3 is equal to 2.3 repeating. So that would be my ratio there. So that's times 2.3 repeating. So that is not a common ratio, so this is not geometric. There is no common ratio. And let's take a look at this example here. Now we need to find the next 3 terms of this geometric sequence and then graph it. So the first thing we want to do is find what is our common ratio. So if I do 12 divided by 18 and simplify that, I get 2/3. If I do 8 divided by 12 and simplify that, I get 2/3. So my common ratio is 2/3. To go from one term to the next, I multiply by 2/3. So let's go ahead and make our table of values again. Recall that my x's are going to be the positions of the numbers. So my first term is 18, my second term is 12, my third term is 8, and I need 3 more terms. So to get remember, to get each successive term, I multiplied by the common ratio of 2/3. So 8 times 2/3 gives me 16/3, or to make it a little easier to graph, 5 1/3. 16/3 times 2/3 is going to give me 32/9, or to make that a little easier to graph, that's actually 3 5/9, which is going to be pretty close to 3 1/2. 32/9 times my common ratio of 2/3 is going to give me 64/27, and that's actually equal to 2 10/27, or pretty close to 2 1/3. So let's go ahead and graph these. And again, I think I'll label my axes here. I'm going to do this, keep my x-axis by 1s. And I think I will do my y-axis by 2s. So I have the point 1, 18, so 1, and then 2, 4, 6, 8, 10, 12, all the way up to 18 would be right there. 2, 12, 2, 4, 6, 8, 10, 12. 3, 8, 2, 4, 6, 8. 4, and that's going to be 5 1/3, so 2, 4, and let's do it about like there, about 5. And 5 and 3, let's call it about 3 1/2, so 2, 4 would be there, 3 1/2 would be right about there. And 6, that would be 2 plus just a little bit, so something like that. Okay? And again, we do not connect these dots. And you'll notice that in this case, this geometric sequence is not linear. I cannot draw a straight line that contains all of those. And in fact, it looks like kind of like it's ending up being a curve. So, one thing you need to notice is that an arithmetic sequence is always going to be linear because you're adding a common difference every time, and a geometric sequence is going to be exponential when the common ratio is positive. An exponential function, recall, is something that kind of slopes towards an asymptote like this, and that would continue doing that. Whereas our arithmetic sequence that we saw here was definitely very linear.